Page 5 now. And notice the index is 5, fifth root. That means, let me just fix this pencil. We're going to multiply by something so that we wind up with a perfect fifth root. Or perfect fifth power. You know what I mean. We want to multiply the denominators together and get an answer that changes to something without a radical sign. So that's an m to the first. What if we used m to the fourth? Because that'll make m to the fifth root of m to the fifth. That'll work. We need the resulting exponent to be divisible by the index, to be divisible by 5. So, multiply this out, we get fifth root of m times m to the fourth is m to the fifth. Okay, so in the next line, we'll be able to get rid of the radical sign. Upstairs, we've got 3 times fifth root of m to the fourth. This power is less than this index, so that's not going to simplify. So it's 3 fifth root m to the fourth power. That's the numerator. And there's nothing much left to do. There's no simplifying in the top. There's not going to be any canceling. So here comes the answer, 3 fifth root m to the fourth. And on the bottom, fifth root of m to the fifth is just m to the 5 divided by 5, m to the 1, or just plain old m. Okay? Oh, I have had students tell me in the past that these exercises with the higher indexes actually make the lower ones kind of more understandable. You understand the strategy better. So here, when we're done multiplying, we want to get an exponent divisible by 7. So maybe you've already got an idea what we need here. We need to multiply the top and bottom of the fraction, of the original fraction, by the 7th root of m to what power will get us up to something divisible by 7? M to the 5th. So after multiplying the denominator here, we'll have 7th root of m to the 2 plus 5 is 7. See how that worked? And on the top, it's just 5 times that radical. Nothing fancy going on there. 5 times 7th root of m to the 5. Final step. Can't do anything with the top. Just copy it. And downstairs, 7th root of m to the 7th will be m to the 7 divided by 7 is 1. So just a plain old m. Okay. All right then. Moving down to number 30. We're back in cube root territory. And this power, of course, is higher than that index. We could work on simplifying that first, but it's kind of more trouble than it's worth. You do want to eyeball these and say, can I reduce this fraction at all? If I made it into one fraction under a single cube root radical, would it reduce? No, it's all 3 different variables. So let's think this way. I'm going to multiply the top and bottom by the cube root of some powers of a and b so that we get a result over here. This is a lot of work, huh? We want the powers of a and b to be both divisible by 3. So 4th power is not, and we're going up, not down, right? So 5th power, no, 6th power. 6th power would be divisible by 3. So to kick this up to the 6th power, I need to multiply by an a squared. b to the second. B to the third would be divisible by 3. So I just need b to the first. This is my now decided upon multiplier. Cube roots of a squared b. Lots and lots of words. Don't blame me if you're getting sick of the sound of my voice. I am myself. This becomes a to the sixth and b to the third. See, now we have what we want, exponents that are divisible by 3. And in the numerator, it's the cube root of, what do we have? P squared, a squared, b. Okay, nothing else we can do with that. And now, let's see, for the denominator, remember the whole idea is finish up with a denominator that does not have a radical sign anymore. So cube root of a to the sixth, that's a to the sixth divided by 3 is 2. And b to the power 3 divided by 3 is 1, so just a plain old b. So there's our answer. Cube root of p squared a squared b over a squared b. Okay. And again, as I said with the numbers, you can't cancel those because that's not really a squared. It's the cube root of a squared. Okay. If we eyeball this, think of putting this under one radical sign. Would it reduce? Yes, because you got 2 and 250. You could divide those both by 2. You got powers of v, powers of b. So let's try that approach. I'm going to first rewrite it as a single fraction under a single cube root radical. Nice and neat, Mr. Dane. Terrible handwriting if I'm not careful. Okay, that's pretty legible, I think. So, excuse me. If I divide the top and bottom by 2, I get 1 and 125. I like that because 125 is a perfect third power. That's the third power of 5. Right? And with the variable parts, remember the old idea of where's the higher power of the variable, that's where it stays. V to the eighth beats v to the second. So we'll have v to the, now we subtract, 8 take away 2. 1 v to the sixth, and what's happening with the b? B to the first, b to the 10th, b to the 10th is the winner. 10, take away the invisible 1. We get b to the 9th. And this is nice because everything is ready to go. This is an exponent divisible by 3, and this is an exponent divisible by 3. That's a perfect cube. That's a perfect cube. So cube root of 1 is 1. I don't need to write the 1 to hold the numerator. V to the 6th cube root is v to the power 6 divided by 3, or v squared. Cube root of 125 is 5, and cube root of b to the 9th will be b to the power 9 divided by 3 is 3. When we're all done, no radical sign whatsoever. V squared over 5b to the 3rd. Moving down to 32 and 33. Earlier we had, I'm covering that up, we had things like this. If we multiply that by the square root of 11, that would take care of rationalizing the denominator. If you multiply the top and bottom of this by square, let me just show you on a piece of scrap paper here. If I jump in there with that same idea, multiply the top and bottom by square root 11, I get 5 square root 11 on the top, and the bottom I'll get 11 plus 3 root 11, I'll still have the daggone square root. It doesn't go away. So there must be a special trick for these, huh? Yes, there is a special trick for these. It's called using the conjugates. When you have a two-term denominator like this, a square root plus or minus another number, or square root minus a square root, anything at two terms in the denominator, remember you can use the conjugate to get rid of the radical sign. What's the conjugate for root 11 plus 3? Just change the sign in the middle, root 11 minus 3. Multiply the top and bottom by root 11 minus 3. And for multiplying out the denominator, feel free to do the FOIL thing if you want, but remember what we did a few pages ago. It's the same two terms, one's plus, one's minus, so we're back to using the old difference of squares pattern. The answer here will be the square root of 11 squared minus 3 squared, and that's 11 minus 9, which equals 2. That multiplies out to a nice simple 2. And for the numerator, I can write 5 root 11 minus 15. Or I could have written this as my answer also. Left that unmultiplied. And thinking about reducing this, we would only be able to reduce this if these two numbers were divisible by the same number. 5 and 2 share no common divisor. So, of course, this is completed. And finally, on page 5, exercise 33. So what are we going to multiply by? The conjugate of root 7 minus root 2, which will be root 7 plus root 2. So, for the denominator, let me zoom out just a little bit here. I'm going to run out of room. Sorry. Using the idea of conjugates as a shortcut, the answer for the denominator will be the square of the square root of 7. Take away the square of the square root of 2. Square of the square root of 7 is 7. The square of the square root of 2 is 2. 7 take away 2 is 5. The denominator is 5. Now, if I multiply this out, I get 10 root 7 plus 10 root 2. If I write it this way, it makes the final step a little easier to do, a little easier to see. You notice we can divide both of these by 5. So let's do that. If we divide this by 5, we get a 2. If we divide this by 5, we get a 1. Well, our answer is not even a fraction anymore. With the 1 on the bottom, we don't need a fraction. We can say our answer is simply 2 times root 7 plus root 2, or 2 root 7 plus 2 root 2. If you use the distributive property, remove the parentheses. Either answer is perfect. End of page 5.